All right, everyone. It's time for us to have a discussion. Now, I've had this discussion with some of my students in the past for the last 8 or 9 years, over the last 9 years or so that I've been tutoring. It's time to talk about the chart. Notice capital THE chart. We're going to talk about the chart so that we can properly analyze functions. And this is going to be really useful basically anytime you're in an algebra setting that's like approaching calculus, and definitely thoroughly in calculus. You're going to need to be able to identify when a function is positive or negative. And so a really convenient way to do that is with this sign chart. Now we're going to keep it pretty simple in this video. I'm just going to show you the basics of the chart and a couple of polynomial examples. But when you do eventually get to a level of calculus, you're going to be using this chart with more advanced functions. So what kind of skills, actually before we talk about the skills, let's just introduce you to the chart. The chart is useful for solving inequalities, particularly when we're looking for when a function is greater than 0. And it also kind of simultaneously tells us if the function is less than 0, where is it less than 0? So analyzing when functions are positive and negative, that's pretty much what that means. Understanding the behavior of rational functions. So I've talked about rational functions a bit. We're going to look at a rational function, a couple of them, actually, as an example. And then we're going to really understand how the chart works. So what does the chart look like? What does it look like? Oh, also wanted to mention, one of the reasons why the chart is really good to know and to master is twofold. First of all, mastering the use of the chart make it easier for you to be successful at higher levels of algebra. But the second thing is that it develops another crucial algebraic technique, and that would be factoring. Factoring is going to become very important in mathematics, regardless of whether or not you learn this chart. So acquiring this skill almost costs you nothing extra in a sense. You're gonna want to be good at factoring anyway. And this will carry throughout into calculus for sure. Okay, so that's what I wanted to say. So what does the chart look like exactly? The chart is basically just like a table, and it organizes your info about the factors of a function, putting each factor into a row. And in that row, we're going to see the zeros of a factor. I'll give you examples, don't worry, but I do want you to write this down. What you should expect. Not only what you should expect to see if you're looking at a chart, but you're going to need to be able to create a chart. We're going to identify where the sign changes occur, like where it becomes positive, negative, positive, that kind of thing. And then we're going to take a look at the overall sign, which is going to be contained at the bottom of the chart, and it's going to take into consideration all of the factors. So really quickly, let's talk about factors. What are factors? Factors multiply, right? So we can have something like x plus 1 times x minus 2 times x plus 5. And each of those parentheses are factors because they're multiplying. So what we might want to know is, when does this function go positive? When does it go negative? We can do that by breaking each of these factors up, or basically breaking the function into these factors, and then looking at when each of those factors is positive or negative. And then we can do a simple kind of multiplication technique that I'll elaborate more on. Okay, so let's look at an example here. On the top, I know this is a lot. It's a lot to take in if you haven't seen this before. What we have along the top, just follow me from top to bottom, yeah? We're going one row at a time. At the top, we have a numbered line. It's the domain. And so the number line goes theoretically from negative infinity, right, all the way to positive infinity. But we really only want to stop at a certain few values. We want to stop at these R1, R2, and R3. These represent the zeros of the factors. So like R1 makes this one 0. R2 makes this one 0. And I don't have any specific x numbers there. I'm just calling it R1. It could be 3, it could be 1/2, it could be square root of 5, it could be whatever it is. It's some number, some x value, and each one of them make the factors negative or positive or 0, right? Oh, well, yeah, I mean the zeros here obviously make each of the factors 0. That's what I meant to say. Okay, so this looks kind of hefty, but let's break down each of these rows one at a time. So what I want to talk about first is analyzing a single factor. When we're analyzing, all right, you ready for this? Listen up. When you're analyzing a single row, we're looking at an individual factor. It's pretty simple. We're just going to take a look at when is it equal to 0. So we usually have to set that factor equal to 0 and solve the equation. And then the general trend is that on the left, we're going to have negatives, and on the right, we're going to have positives. That's generally the trend here. So I'll just show you that really quickly on a basic numbered line with this linear factor x minus 3. So for x minus 3, when does this thing equal 0? If we set it equal to 0, and we solve that x minus 3 equals 0, then we get that x equals 3. So there we have it. That's one of the zeros. Well, it's the only 0. And therefore, on this numbered line, which goes from negative infinity to infinity, I want you to realize that if I plug in 3, I get 0. If I plug in anything bigger than 3, like this way, anything bigger than 3, and I get a positive because x minus 3. If I plug in something bigger than 3 and then subtract 3, it's going to be a positive. I don't really care what the exact number is. I just care that it's going to be something positive. And if I plug in less than 3, like if I plug in 2 or even 2.9, and I do minus 3, that's going to give me a negative. So you see this basic pattern is to the left, it's going to be negative. To the right, it's going to be positive. Very simple, right? And you can just confirm that with yourself every time. I want you to do that since you're just getting started with this. Right where your zero's at, and then ask yourself, what happens if x gets bigger? That's all you have to ask yourself. What happens if x gets bigger? Well, if x gets bigger, then when I subtract 3, when I do x minus 3, it will still be positive, okay? And if x is smaller than 3, when I subtract 3, it will be negative. Makes perfect sense. Now let's look at something with a negative coefficient. Maybe one of your factors has a negative on it. There's two ways to deal with it, but I'm just going to show you the basic way here. We're again going to find the 0. When does it equal to 0? And that will be a couple of quick steps. That means we can add 3x on both sides, and then we can divide 3 on both sides, and we get 1/3 equals x. There we have it. That is where the 0 happens. But then you have to ask yourself, what happens if x gets bigger? Look at the original equation. If x gets bigger, then we're multiplying it by a negative. That means it's going to get smaller, like more negative. So if I plug in x is bigger on the right side, I actually get that it's going to be a negative, you see. So the sign behavior flipped from this one. This is normal sign behavior because there's a positive on the x. When I plug in a bigger number, I get a bigger value. But in this other case, with a negative on the x, if I plug in a bigger x number, I actually get a more negative result, okay? So the behavior switches, and that's a note that you can write if you want. Negative coefficients are going to flip the sign behavior compared to the positive coefficients. Okay, so this is just looking at one row of the chart. Each one of these factors is going to have their own row. And so the chart, if we look back at this again, I'm really just kind of stacking these rows together and putting them all using the same number line. And so different factors will have different zeros, and we'll look at the behavior here. See, this is negative on the left, and then it's positive on the right. Negative on the left, positive on the right. Negative on the left, positive on the right. Now, there are some rules that you need to keep into consideration, but let's just start with that for now, okay? Let's look at some polynomials here. Here's a polynomial function. It's not expanded. It's in factored form because it's a 6th-degree polynomial. I would not want you to have to factor that down from an expanded form, and I wouldn't want to write the expanded form. What we're going to do here is we're going to look at some of the zeros and look at some of the factors, but I want you to notice that some of these factors are repeated. This one is repeated. This is x minus 1 squared, right? So because it's squared, it has this very interesting behavior. When does that equal 0? That equals 0 when x equals 1. But I want you to realize that if I put that on the chart, x minus 1, and I put a little arrow 2 here to say that it's squared, it's going to equal 0 when x equals 1. However, it's not going to equal negative on the left. It's going to be positive on the left and the right. Do you understand why? Because x minus 1 squared, if I break this into two separate factors, if I graph x minus 1 and x minus 1, and I'm explaining this because it's kind of how all the entire system of using the chart works. If I have my number line here, something special happens at 1. We get 0. We get 0. To the left, we get negatives because they are linear factors. And to the right, we get positives. But if I multiply that together, what I'm actually looking at here is that if I have x is less than 1, I'm multiplying a negative times a negative. I'm doing a negative squared. And so that's going to become a positive. And therefore, because of that even power, it turns those negatives into positives when we multiply them together. So that's why we see that the x minus 1 squared factor just has positives the whole way. And then it has the 0, of course, when x is equal to 1. All right. Now let's look at x minus 2. That one's not anything special. It's just a normal factor of x minus 2. So there's going to be a 0 at 2. It's negative over here. It's positive over here. Okay. Let's see. So this was when x equals 2. Then we have when x equals negative 3, something special happens. That factor is equal to 0. So here's the bottom factor, x plus 3. It's cubed. It's actually cubed. We get a 0 here. And what's happening? We see that the sign does change. Does that seem to make sense? Because it flips to positives everywhere when it was even. And it seems to be flipping back to the same kind of behavior as if it didn't have a power on it at all. Meaning there's just like a 1 power. So let's make sure this is consistent. I'll do the same kind of thing by breaking down those 3 factors separately. If we have x plus 3, we have x plus 3, and another x plus 3. At negative 3, these are all equal to 0. And they each, since they are linear factors, have the left negative and the right side positive. And so if you plug in something that's less than negative 3, the overall result will be a negative times a negative times another negative. So a negative times a negative is positive, but then times another negative gives us a negative. The 0, 0 times 0 times 0, and then we have all positives being multiplied. So you kind of observe this behavior, that if it has an even power to it, it's going to stay positive on both sides of the 0, and if it has an odd power, then it's going to be switching. It's going to flip. And if this were a negative on the inside, it would flip everything just like we saw in the single factor case. All right, so let's talk about the overall signs here. Well, we know that if any one of these factors is 0, again, remember, what's a factor? A factor is something that's being multiplied together. These things are all being multiplied together. And so if either one of these things is 0, the whole product is just 0. Because if one of these things is 0, it's just 0 times something else. Doesn't matter what that something else is. Right? So if any of those factors are equal to 0, then the whole function is equal to 0. So we have 3 values where that happens. That would be at -3, that would be at +1, that would be at +2. Remember, these are x values. These are the intervals. So what we would say is that this is going to be positive, then we have negative, then we have still negative, then we have positive. And I'll show you how to sketch this graph in just a moment. First, we're going to take a second to really think about this domain idea. Love talking about domain. It's a very useful thing. And now that we're pretty experienced with drawing intervals at this point, we can say that the function is positive, or I guess you could also just say f of x greater than 0. That's the right way to say it. And we say on the following intervals from -infinity to -3, and then it's positive again from 2 to infinity. Now, I didn't put brackets on these because it's not positive at those values. We also can't make it to infinity, but I mean -3, when we get to -3, it's not a positive function value, it's a 0 function value. And then the function is negative, which means f of x is less than 0 on the interval from -3 to 1, and union from 1 to 2. I know it seems like I should be able to just connect those together, but there's something special happening at 1 where the function is equal to 0, not a negative. Okay, now let's talk a little bit about the graph, because it's really important to know how to sketch some of these graphs. It's a dying skill. We already pretty much have the number line with the location of the zeros, so just read that. We have 2, 1, and -3. So this is going to be our -3, I guess. There's our 1, and there's our 2. Now the sign chart tells us about the values of the function. It tells us that it's positive all the way up until x is -3. So that means it like goes up there somehow, right? Goes like way up there. But you also have to consider the fact of the power. It's a cubed. So it's going to make kind of like an x cubed sort of shape. It's going to like kind of go flat and then go down again. Does that make sense? Then this chart says that the graph is negative all the way until +1, where it hits the 0. It's going to go down here. We don't know exactly how far down it's going to go, but we know that it's going to go down. Where does it flip there? Yeah, something like that. It hits the 0. And then what happens? This chart says that the function goes negative again until x equals 2. So it kind of makes like a swoop, and then it goes through x equals 2. Now let's confirm the behavior of this one here at x equals 1. It's going to make an x squared shape because the power is 2. Get it? So when x equals 1, it goes to 0, but it has like an x squared kind of bounce to it. Or in this case, since it's -0, negative, it's like an upside down kind of shape to it. That's exactly what happens here. It makes an x squared kind of shape right there. And then since the x minus 2 factor was with no special power, it just went straight through like normally. Now here's what we don't really know about the graph unless we plugged in numbers. We don't know exactly how far down this goes. It's likely that it goes very far down. We could find the y-intercept by plugging in 0, and that's fairly easy to do. And I'm kind of curious, so let's go ahead and do that. So 0 minus 2 times 0 minus 1 squared times 0 plus 3. So -2 times 1 times 3. So it wouldn't be down too far. It would be down at -6, but that's still probably lower than I drew it. So it'd probably be something more like that. But you get the idea that we know the general shape and we know this little bends that it makes here on the function. And particularly we know when it goes through the zeros and we know when it's positive or negative. Okay, so let's move on to a rational function. I like talking about these revisited topics. I like talking about these kinds of Algebra 2 review topics because you need to have really solid Algebra 2. Like obviously your pre-calculus needs to be pretty good. Only makes sense that it's in the name pre-calculus. But your Algebra 2 needs to be excellent because that's from even further back. That's from prior to pre-calculus. So you need to be comfortable with this. Let's take a look. We have a rational function, and this one's going to have holes, and it's going to have an asymptote. So one thing that I didn't mention yet is that when one of our factors is in a denominator of a fraction, the zeros mean something different, right? So let's just write that here, make it smaller. Zeros in the denominator in an undefined function value. So like if the denominator is 0, then that's going to give us a vertical asymptote sometimes. It's going to give us some kind of a problem here. So on the top, finding the zeros and the restrictions, on the top, it's clear that x equals 2 is a factor. Is a 0 because x minus 2 is a factor. And x equals -3 is also a 0. And that's because x plus 3 is a factor on top. But on the bottom, we need to factor the bottom. If we factor the bottom, x squared plus 2x minus 3, we can write that as x plus 3, x minus 1. And so there's a common factor there. Therefore, the 0 in this denominator is going to be x equals 1 as well as -3. So our restricted values are going to be 1 and -3 because we cannot have the denominator be 0. These are domain restricted. Okay, let's analyze some special points. Now we're just breaking this down into factors. The top of it was already pretty much factored for us, which is nice because I really just want to introduce you to the chart, how to put things on the chart. We'll worry about factoring techniques in another video. This is mostly about the chart. That's why I also kind of graciously had this already factored for you. So let's take a look at our special points. We have a hole based on this common factor of x plus 3. So therefore there's a hole at x equals -3. And then how do we find the y value of that hole? Well, what you need to do is you need to cancel the common factor, then plug in the restricted x value. Let's see, let's make this like that. Let's also make this smaller. Eso. Okay, there we go. So we're going to cancel the common factor of x plus 3, and then we're going to plug in the x value that is restricted, which is -3. So what does it look like when we cancel the x plus 3? We're going to have x minus 2 squared over x minus 1. And if we plug in x equals -3, this is going to turn into -3 minus 2 squared over -3 minus 1, which is -5 squared over -4, and that gives us -25 over 4, which is about it's exactly -6.25. Not the nicest number, but that gives us the y value, the location of the hole. Okay, let's take a look at the vertical asymptote. That's going to be where the other value is 0. Remember, our two restricted values, these were our factors for the restricted. one of them canceled, x plus 3 canceled, and that gives us the whole. And then x minus 1 is still there, which gives us an asymptote at x equals 1. Because that will make this denominator factor equal 0, which will make the whole denominator 0, which makes the fraction undefined. So we have some info, some really useful info. I should probably start boxing this stuff. We have that. We have the x and y value of the whole. We have some zeros, so we know where it crosses through the actual x-axis. And of course, this is not a 0. It would be if it didn't cancel with the denominator, but instead it contributes to a whole. So far we have quite a bit of stuff. Now let's put this on the chart. We have x minus 2, that factor is squared. And therefore it does equal 0 when x equals 2. But it's going to be positive everywhere else, right? We talked about y. It's an even power. So if you were to stack those two lines on top of each other, those two rows, it would just be a negative times a negative, which is positive, or a positive times positive, which is positive. Now for this factor, this is a special factor because it's on the top and the bottom. This is the one that canceled. And so when x equals negative 3, it doesn't really quite equal 0 because the top does equal 0 and the bottom does equal 0. But what does that mean for the overall fraction? That means there's nothing going on there. It's really weird there because you can't divide by 0. However, it does follow the same pattern, by the way, that it's plus everywhere, except for where it's 0. Why is that? Because x plus 3 over x plus 3 is always equal to 1, except for the spot where it's undefined. And lastly, we have x minus 1, which is equal to 0 when x equals 1. It's negative on the left, and it's positive on the right. But remember that overall, that means that x equals negative 3 and x equals positive 1 give us a undefined value. It does not exist. So I can't say it's 0, negative, or positive. It just doesn't exist. Now on the left side, we have negative, 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 and then it goes undefined. And then we have negative, negative. By the way, this one is the whole. And this one is the vertical asymptote. So then we finally have positive, positive, and positive, positive. Okay, so if we wanted to sketch this, we'll interpret the results as well. The positive intervals, when is this positive? We'll say f of x is greater than 0, which means positive, on the interval from 1 to 2, then it crosses through 0, and then from 2 to infinity, it's positive again. The negative intervals, when f of x is less than 0, that is on the interval from negative infinity to negative 3, and then there's nothing. There's a blip at negative 3, and then from negative 3 to positive 1. That's when this function is negative. Okay? So just a reminder that to find the y value of the whole, we have to substitute the x value that's restricted into the simplified form, the reduced form of the fraction. And that gave us, like I said, about negative 6.25. And near the asymptote, what happens, behavior near the asymptote of x equals 1? Well, it's going negative on the left side, which means it's going down to like negative infinity. And then all of a sudden it comes positive from the top. Yeah, so if we took a sketch of what that kind of looks like, we'd have a crossing point at 2. That's where it would cross the x-axis. And then we would have a vertical asymptote at x equals 1. And then if we wanted to find something like a y-intercept, we could plug in 0, which I probably should have mentioned back here, but we can plug in 0 to find the y-intercept. That's one of our special points as well. So that's going to give us 0 minus 2 squared, 0 plus 3, over, well, all that just turns into negative 3. So 0 plus 0 minus 3. Okay, perfect. So what does that give us? Negative 12 on negative 3 or 4? That gives us a 4. Let's see if this is reasonable here. Oh, sorry. This would give us negative 4. Because we have a positive 4 times 3. And that matches our chart, right? Our chart says that from negative 3 to 1 should be negative. So, yeah. Makes sense that we have this y-intercept at negative 4. How can we do it? Maybe something like that. And then where's the whole location, which is at negative 3, negative 6.25. So that's going to be something like that. So I'm going to guess that this function does this. It comes up to some kind of a peak, but we don't really know how high it goes unless we wanted to plug in some values. So if you want to plug in negative 2, if you want to plug in negative 1, we would be able to figure out a little bit more accurately what this sketch looks like. And then let's take a look at what's happening here at x equals 2. The function goes from positive down here, and then it stays positive. So up, something like that. Now, when you get to a calculus level, and for those of you who are watching that are in calculus, you're going to have to know how to find these maximum and minimum points. That's what they're called, maximums and minimums. But for folks that are in lower levels that are approaching calculus level, not quite there, this is pretty much as specific as we can get. Now, for those who are in calculus, you're going to be looking at these charts as useful, particularly when you're trying to figure out if the derivative's positive or negative, or if the second derivative's positive, negative. It's going to really assist you with things like increasing, decreasing behavior, and concavity. For those who that doesn't really mean anything yet, for a couple of years, that's okay. This chart's going to be used heavily, especially when prepping for calculus, when you're getting prepared to step into calculus. You're going to want to analyze things with this kind of a sign chart. And the reason why I'm showing you this is because you're not going to see this, generally not going to see this in a class. Like, they're not going to show you the chart in a calculus class or anything like that. If you show your professor the chart, they're definitely going to understand it and they're going to appreciate it. And they'll say, yeah, that makes sense. But they might not necessarily teach that. And I think that's kind of a flaw, which is part of why this video is so important. So yeah, recommend it to a friend who sucks at factoring or is really bad at telling if functions are positive or negative. And we'll be using this heavily next time.